When one object collides with another, they exchange energy and momentum, and the two objects will accelerate, either speeding up or slowing down or changing direction. Any exertion of energy that attempts to make an object accelerate or actually makes an object accelerate is a force. A simpler definition would be that a force is a push or a pull on an object. If an object accelerates in any way, it needs some kind of force to act on it. For a force to act on an object, there has to be energy. So all three concepts, energy, motion, and force, all tie together and work simultaneously on us and all the objects around us. A force always tries to move an object in one particular direction, and will usually be shown as an arrow pointing in that direction. Since forces not only have a magnitude or strength, but also a direction, and since most objects have multiple forces acting on them, if we're going to determine how the forces acting on an object will affect its motion, we must pay very close attention to the directions of each force. During a tug-of-war match, both teams are exerting a lot of force, but no one moves very much, because the forces are going in opposite directions and cancel each other out. Any change in the state of motion of an object, if it accelerates in any way, is the result of the sum or total of all the forces acting on it. The sum of all the forces acting on an object is called the net force. The scientist who figured out how force relates to motion was Sir Isaac Newton. So, in honor of him, the unit used for force is the Newton, or a capital N. To figure out how the forces acting on an object will affect its motion, we have to find the net force. So, we have to do some basic adding and subtracting. Forces that act in the same direction add together, and forces that act in opposite directions take away from each other. Forces acting at angles can partially add or subtract from each other depending on the angle. In these cases, you would assume that the arrow representing the force is the hypotenuse of a right triangle and break it down into its vertical and horizontal components, viewing each as a separate force. We won't work with any of these here though. Looking at the truck here at the center of the page, we can see that there is a 100 Newton force working to the right and a 60 Newton force working to the left. Since those forces are working in opposite directions, they take away from each other. So 100 minus 60 leaves us with a net force of 40 acting to the right. This means that the truck will accelerate to the right. Towards the bottom right of the page, there are some other examples of forces or combination forces that we can use for practice. After all the different forces acting on an object have been added together, after you've found the net force, if you find that it works in one particular direction, that is the direction that the object will go. But if the net force adds up to 0, then the object will not move at all. Two of the most common and important forces are friction and gravity. They work constantly on every object on Earth. Gravity works whenever two objects with mass are near each other, and friction works whenever two objects touch each other. You and the computer, you and the walls, you and the Earth, all exert gravitational force on each other. Your feet in the ground, your body in the air around you, your clothes and your skin, all have frictional forces working between them. Friction only works when objects try to move. If two objects are touching and a force is applied to try to make one move, friction will work in the opposite direction as that force to resist movement. If you put your hand on a table and slide it to the right, friction is pushing left. If you try to slide it left, then friction will push right. If the force of friction is strong enough, the object won't move. Friction strong enough to keep an object from moving is called static friction. The word static refers to not moving or not changing. If you push harder, exert more force, eventually overcome static friction, and make the object move, you'll still have to deal with friction. Friction works on a moving object is called kinetic friction. You may hear this term broken down into specific types of kinetic friction, such as sliding friction or rolling friction, but they're just types of kinetic friction. Say a car you're riding in breaks down, and you have to push it to the side of the road. The car is stationary, you get behind it and start to push. You push as hard as you can, rocking it back and forth a few times before it actually starts to move. Once it starts to move, it is still tough to push, but not as difficult as when you're first getting going. When you first started pushing, you're trying to overcome static friction. Once you pushed hard enough to overcome static friction, it started to move easier. You still had to push against kinetic friction, but because it's not as strong as static friction, it was easier to keep moving than it was to start moving. The strength of friction depends on how much the objects are being pressed together, usually weight pressing it to the ground, and the structure of the surfaces in contact. If you put your hand on a desk and slide it, it moves easily. However, if you press down hard on the table and then try to slide it, it's more difficult. By pressing your hand down on the desk and increasing the friction between the two objects, it made it resist motion more. Large objects with a lot of mass are pulled down to the earth by gravity more than small objects, so they're pressed harder and as a result have more friction. Similarly, the rougher a surface is, the more friction it will create. Smooth, light objects have the least friction, while heavy, rough objects have the most. Since friction is fighting motion, the energy used overcoming friction when you try to make something move is just wasted energy. Most machines are built with this in mind and have designs to minimize friction, usually by adding lubricants. For example, the oil in a car is meant to reduce friction. Also, in most of your joints, you have synovial fluid, which reduces the friction of moving bones and allows them to move easier. Gravity is the attractive force that works between any two bodies with mass. It does not matter if you're talking about the sun, a planet, a giant boulder, a person, pen, or atom. All objects exert gravitational force. There is gravitational force pulling between every object in the universe at all times. Earth is pulling on you, Mars is pulling on you, your computer, tablet, or phone is pulling on you, and you're pulling on each of them. The reason you fall to the Earth instead of to your phone or to Mars is because the strength of each of those pulls is different. The law of universal gravitation, written by Sir Isaac Newton, states that gravitational force increases as mass increases and the distance between objects decreases. This means that the closer objects are to each other, the stronger the gravitational attraction between them will be. Similarly, the bigger those two objects are, the stronger it will be. You're much closer to the gravitational center of the Earth than to the gravitational center of Mars, so the pull between you and the Earth is stronger than between you and Mars. Compared to the size of a planet or a star, you and your computer are very small, so the attraction between you is very weak, too weak to make either of you move. However, the Earth is big enough and close enough to you for the attraction between it and you to be strong enough to move you. If you don't hold on to something or push off something, you will fall toward the center. The force of gravity between you and the Earth is your weight. Since the force of gravity depends on mass, the two will increase and decrease together, which explains why people often use the words weight and mass interchangeably even though they describe very different things. Weight is a force, mass is the amount of matter. How fast an object falls is a result of the force of gravity. As an object falls, it gets closer to Earth, and part of the law of universal gravitation says that the closer objects are to each other, the stronger the force of gravity becomes. So, as it falls, the force of gravity increases. Increased force means that the object will accelerate. If it was thrown up into the air, the force of gravity would still be pulling it down, which means that it will eventually slow down and begin to fall. If the object went high enough and the distance between the object and the Earth increased significantly, the force of gravity would decrease and eventually not be strong enough to make the object move. This is why astronauts are weightless in space. They are too far away from the Earth's center for the gravitational attraction between them and Earth to make them fall. Objects that do fall all accelerate at a constant rate, ignoring wind resistance. Wind resistance, which is friction between an object and the air, will slow an object's descent and eventually be strong enough to make an object stop accelerating. But for now, we'll pretend that we're working in a vacuum without wind resistance. A falling object will increase its velocity by 9.8 meters per second every second it falls, meaning that it has an acceleration of 9.8 meters per second squared. The velocity of a free-falling object at a particular time is just this value multiplied by how long it's been falling. In the equation, v means velocity, t means time, and g means the acceleration of gravity, or 9.8 meters per second squared. So delta v, or change in v, equals g times t. This value of gravitational acceleration is pretty much constant on Earth. So if an object was thrown up, gravity would still be pulling it down. This means that it would be accelerating the opposite direction, so its speed would decrease. You could say that a ball thrown up in the air accelerated at negative 9.8 meters per second squared on the way up, and 9.8 meters per second squared on the way down. Orbital motion, the movement of objects around stars and planets, is the result of the net force acting on those objects, one being gravity, and the other being the motion the object had prior to when it started orbiting, inertia. Projectile motion is also based on gravity. How far a ball thrown forwards goes before hitting the ground is decided by the net force of gravity pulling it down and the force pushing it forwards, which in this case would have been how hard it was thrown. The harder something is thrown horizontally, and the higher it's launched, the further it can travel before being pulled back down to Earth.